it's a great pleasure to introduce Paul Hacking from UMass, who is going to tell us about the formations of Cusp Singularities and mirror symmetry. Paul?
Yeah, thanks very much for the invitation to speak. And I believe I'm the last speaker, so perhaps we should first thank the organizers, Luville, Philip, and Carlos, for a very nice conference.
Thank you.
I certainly enjoyed it very much myself. I really enjoyed the collaborative atmosphere. I want to talk about deformations of cusp singularities, and in particular, so a cusp singularity is a singularity that can arise on a singular surface at the boundary of the KSBA moduli space. So that's been an object of study of this FRG group, sort of trying to understand that KSBA moduli space in terms of Hodge theory. And sort of I thought about cusp singularities for a while from the point of view of mirror symmetry. And I sort of was listening to the talks this week, and I feel that the case of cusp singularities deserves some study. It seems to me that it provides maybe a non-trivial test of this conjecture of Green, Griffiths, Lazar, and Robles that the there's a map from the KSBA space to some version of the Bailey-Burrell compactification of the image of the period mapping. In the case of cusp singularities, that looks quite non-trivial. So I think maybe that's the take-home from this talk. I'll try to give an overview of what's known about cusp singularities and their deformations. A lot of it is not my work. In particular, should certainly mention Friedman and Engel. But the parts of it that are my work are joint with Mark Gross and Sean Keel, Ailsa Keating, who's a symplectic geometer, and my graduate students are Jennifer Lee and Angelica Simonetti. Maybe I just ask if there are any questions before I begin the main talk. I also wanted to mention that I believe, Daniel just posted in the chat, I've sent a link that I hope you should be able to just see my slides at that link, in case you prefer to just read the slides instead of listening to me talk. Okay, but anyway, let me get started then. So first of all, what is a cusp singularity? So maybe I'll make my screen a bit bigger here. So it's a normal surface singularity, an isolated surface singularity normal, such that when you take the minimal resolution, the exceptional divisor E is a cycle of P1. So it's a nodal union of smooth rational curves such that the dual graph is a cycle. And I guess there's sort of a special case as well where you just have a single rational nodal curve. So an example of a cusp singularity from the point of view of algebraic geometry would be the hypersurface x to the p plus y to the q plus z to the r plus xyz is equal to 0 inside C3. And you can see this is a cusp singularity because if you just blow up the singular point, which is the origin in this case, you'll extract xyz equals 0 inside P2. That will be the exceptional divisor of that partial resolution. So you'll have a triangle of rational curves. But at the nodes of that triangle, there'll be some type A Duval singularities. And if you resolve those, you'll get this cycle, which is the exceptional locus of the minimal resolution. So that's an example of a cusp singularity. Oh, and I should have mentioned maybe, for this to be valid, you need 1 over P plus 1 over Q plus 1 over R, strictly less than 1. Questions so far? Okay, so let's mention some key facts about cusp singularity. So first of all, the Gorenstein, the canonical divisor, is trivial. They're log canonical. So this is the statement that when you take the resolution, the discrepancies, so if you look at the difference between the canonical divisor of the resolution and the pullback of the canonical divisor, that's a linear combination of exceptional divisors, the coefficients there should be greater than or equal to -1. And that is the case here. In fact, they're all equal to -1. So kx tilde plus e is trivial along the exceptional locus. So this is the reason that we see it in the KSBA moduli space. It's a log canonical singularity, provided there is, in fact, a smoothing. And maybe also mention, so as we've heard this week, the Gorenstein case is the case where you see some interesting Hodge theory associated to the degeneration. Yeah, and the final remark is this is what's called an elliptic singularity. So if you look at the higher direct image of the structure sheaf of the resolution, you just get a skyscraper sheaf at the singularity with stalk C, so one-dimensional vector space. And just to sort of warn you, these singularities are pretty complicated in the sense that I just gave an example above, which was a hypersurface. But in fact, there are examples of arbitrarily high multiplicity and embedding dimension given by these formulas in terms of the resolution for a smoothable cusp singularity. So even if you only care about the smoothable case, so you're interested in this moduli question, you're going to have to worry about arbitrarily large multiplicity and embedding dimension. Okay, that was my first section. Any questions about the first section? So second, yeah, so that's a description of a cusp. So in terms of algebraic geometry, it's high embedding dimension. It's hard to understand, but there's a completely elementary construction in terms of toric geometry due to Hertzebruck. So this was discovered during his study of the Hilbert modular surfaces. So you take a matrix in SL2Z, which is hyperbolic, so by which I mean the trace is strictly larger than 2. So we've got 2 positive real eigenvalues, one of which is bigger than 1, then you have the inverse, of course. So let's let V and W be 2 the eigenvectors for those eigenvalues, and let's choose that so the basis VW is positively oriented. Note that those are going to be irrational vectors in R2. Now let's look at the open cone spanned by V and W. And we consider this set U, a so-called tube domain, inside the algebraic torus C star squared. So it's the part, if you regard C star squared as C2 mod Z2 via the exponential map, it's the part where the imaginary coordinate lies in this cone C. Okay, so then you have this picture that the matrix A is going to act properly discontinuously on this set. I'm sort of drawing this picture here. So it's a hyperbolic action in this sense. So this is the action on the cone, and then you have the corresponding action on the set U. So you can take the quotient and get a complex analytic space, and that's a punctured neighborhood of the cusp singularity. So in particular, you see that from this description, cusp singularities correspond to conjugacy classes of hyperbolic elements in SL2Z. Okay, and so from this picture, just to connect with what we said before, you can describe the resolution. So you look at this open cone, you take the convex hull of the integral points in that cone. So that will be an infinite polyhedron, an infinite polygon, and you just take the fan with support, the cone C, and its rays generated by the integral boundary points of that polygon. So maybe I think I have a picture down here. And now so this gives me some fan in R2. I take the corresponding toric variety, so it's an infinite type toric variety, infinitely many affine patches. Now, if I take a tubular neighborhood of the boundary of that toric variety, again, I have a properly discontinuous action on that tubular neighborhood. And if I take the quotient, I will see this cycle of P1s, which is the exceptional locus of the minimal resolution of the cusp. So this sort of explains what this has to do with the other definition in terms of the minimal resolution.
A quick example, if it's really easy, that example, hypersurface example you started with, is it easy to see which elements in SL2 they correspond to?
I'm afraid I don't know off the top of my head, Valerie. But I guess it will be contained in the rest of the talk implicitly, at least. So maybe I'm sorry. Yeah, I don't know off the top of my head. Okay, so let me just remark. So this is kind of important for what follows. That by this construction, the Hertzsprung construction of the cusp, the punctured neighborhood of the cusp has a smooth C infinity torus vibration. So T2, the real 2 torus, over a punctured disk with monodromy, this matrix A. So that sort of gives you a smooth description of a punctured neighborhood of the singularity. So in particular, the link of the singularity, so the intersection with a small sphere in some embedding, will be a torus bundle over the circle, 2 torus bundle over the circle with monodromy matrix A. Okay, so let's see. Are there more questions at this point? Okay, so not all Cusp singularities are smoothable, but there's a completely elementary description of which Cusp singularities are smoothable. This was a conjecture of Lienga in the 80s, who proved one direction. So the necessity of the condition, and it took a while before sufficiency was proved. So eventually it was proved by myself with Gross and Keel, and also by Phil Engel. So we used some ideas coming from mirror symmetry. But let me explain the elementary characterization first of all. So we say that a cusp is a cusp is smoothable, meaning it has a deformation to a smooth surface, precisely when you can factorize the monodromy. So you have this element of SL2ZA, and you can write it as a product of simple shears such that the invariant directions of the shears are arranged in cyclic order. So here's the sort of picture of what's going on here. So yeah, so I've drawn on the right. So you should think about, there's this base, which is a disk, and you've introduced some branch cuts along the rays in directions V1 up to Vn emanating from the origin. So this is supposed to be the base of a torus vibration over the disk, which is a deformation of the torus vibration over the disk on the cusp singularity itself, which has this fiber over the origin, which is just a single point. So you've sort of perturbed that singular torus vibration to get one which has only ordinary singularity. So over each of these points in the base, the marked points X in the base, we have a pinched torus fiber, and we have the usual picture of the Picard-Lefschetz monodromy around that singular fiber. So this simple shear. And this condition, on the product is just saying that the total monodromy at infinity is the product of these local monodromies. Okay, and so that's a condition that one can check. There's an algorithm to check this to see whether or not a cusp is smoothable. Yeah, so what I was trying to say, maybe I have a bit more here, is so this Milnor fiber, so the nearby fiber of a smoothing, has now this topological description as a 2 torus bundle over a circle with a certain number of ordinary singular fibers, pinched tori. And maybe just to explain where this picture comes from in the plane, from in symplectic geometry. So the Milnor fiber is, of course, embedded in the ambient Cn of the Cusp singularity. So it's an exact symplectic manifold. You can just take the restriction of the symplectic form on the ambient Cn. What we have here is a Lagrangian torus vibration. So the restriction of the symplectic form to the fibers, the torus fibers, is trivial. As I said, with these singular fibers over these points in the base, and the vanishing cycle is identified with this vector in Z2, because the coordinates, the integral coordinates on the base, or the integral points on the base, you can identify those with the H1 of the central fiber of this torus vibration. So this is an instance here, maybe I should back up a little bit, of what's called the Arnold-Luville theorem. So if you have a Lagrangian torus vibration over a base, you get a so-called integral affine structure on the base. So that's so the base is a smooth manifold. It have an atlas of charts for that smooth manifold, where the transition maps are given by integral affine linear transformations. So the matrix is an integral matrix. So constant transition functions such that they're given by affine linear transformations. Okay, and so in that how does that structure arise? Well, one way to describe it is in terms of the local coordinates in this integral affine structure. So you can write down the coordinates in one of these charts in the following way. So you just pick a point in the base, and you pick a basis of the cohomology, the H1 of the fiber, and then you write down these functions on the base, the integral of the symplectic form over a cylinder traced out by the chosen cycle on the reference fiber. And those will give you sort of locally well-defined coordinates on the base. So here, I guess we're using the fact that omega is closed and the fact that the fibers are Lagrangian to show this is well-defined. And this is a way to describe this integral affine structure on the base. Now, let's just sort of look at the sort of case of just near one of these singular fibers. So that's what's happening in this picture. I've sort of introduced a branch cut. So that in our picture, it was going off to infinity towards the boundary of the disk, so that the integral affine structure is discontinuous over the branch cut, but everywhere else it's continuous. And so I have sort of two charts in a little neighborhood for my integral affine manifold here. And they're related in this way, where so somehow you have a piecewise linear map, which is the identity on the lower half plane, and it's given by the shear B, the Picard-Lefschetz transformation on the upper half plane. So that's the picture of this, the geometric interpretation of this condition. It's the structure you see on the base of a Lagrangian torus vibration of the Milnor fiber of the smoothing. Okay, so that was a lot of information, and I know most people here are algebraic geometers, so maybe I just ask if there are any questions or clarifications required at this point.
So, Paul, you might have more than one smoothing, right? You were
That's
saying
right. Yeah. So actually, maybe I just mentioned it in connection with your talk, Giancarlo, the other day. Yeah, there are more than there are many examples. We have more than one smoothing component. So that can often be distinguished by the topology of the Milnor fiber. And so yeah, absolutely, you could sort of connect different KSBA moduli spaces in this way, conceivably.
And how you compare the Milnor fibers in those two different?
Yeah, let me just say, I've got a little bit more here. I didn't say too much. So it's easy, using this picture to describe the topology of the Milnor fiber. So you can see that it retracts onto a real two torus union, the n disks swept out by the vanishing cycles, the so-called thimbles traced out by the vanishing cycles. And so then, just looking at the homology of that space, you see that its a fundamental group is the quotient of the lattice by the integral span of those vectors. So that will be a finite cyclic group, but it's not necessarily trivial. So that's one invariant. And of course, the Euler number, because we have this torus vibration, is just the number of singular fibers. And so, to get towards Giancarlo's question, the Euler number does not depend on the smoothing. So if there's more than one possible way to smooth, this number n is constant, and it's a little bit like a sort of, Kontsevich-Soyleman called it a integral affine Gauss-Bonnet theorem, that somehow, when you have this picture, the manifold is essentially flat except at the singularities, and there's some sort of positive curvature contribution at each singularity. And so somehow, that's why this Euler number somehow, is a sort of well-defined, just defined by the sort of monodromy at infinity. On the other hand, the fundamental group can be different. So I guess maybe I should give a quick example. Let me see if I can do that right now. So example would be, so there's a similar picture for simple elliptic singularities. So there the matrix would look like this. So it'd actually be unipotent, where n is the degree of the simple elliptic singularity. So it's the cone over elliptic curve of degree n. And in the case n equals 8, so we know that the Milnor fiber is always, for a simple elliptic singularity, it's always the complement of a anticanonical elliptic curve on a Del Pezzo surface. So it's either, in this case, P1 cross P1 minus elliptic curve, or the blow of P2 in a point minus an elliptic curve. Yes, I should say so. So somehow the Del Pezzo, again, the degree of the Del Pezzo is the same as the degree of the elliptic cone. And so here, of course, the 2 pi 1s are, in the first case, Z2, and in the second case, trivial. So that's an example of this phenomenon, that the fundamental group can depend on the, give myself a little bit more room here. Oops. Yeah, so maybe I just quickly draw those two pictures of the vectors in that case. So here are the vectors. Maybe this is a good example for Valerie. That's the Z2 monodromy. And the other one looks like this. I hope it's clear. These are pictures of the vectors in the plane. So this is Z2. Good. Okay, so let me continue. To go a little bit further, I need to say a little bit about mirror symmetry. I know that's not the main subject of this conference, so I don't want to say too much about mirror symmetry. But it is good to understand the full picture, to know a little bit about it. So this Milnor fiber that we've just described is mirror, in the sense of mirror symmetry, to the complement of the boundary in a log Calabi Yau surface. So that's a smooth projective surface Y, together with a normal crossing boundary divisor D, such that ky plus d is equal to 0. So if you remove d, you have k trivial. This is a Calabi Yau, an open Calabi Yau. And so you can think about this as an open Calabi Yau manifold where you've got some kind of control as you go off to infinity. Okay, and so kind of a very nice thing is that, given this picture we described for the Milnor fiber, one can construct this mirror very explicitly. So remember, in the picture for the Milnor fiber, we had this fan of vectors in the plane. We just write down the corresponding toric surface together with its toric boundary associated to that fan. And now for each of those singularities, we blow up along the corresponding boundary divisor of this toric surface y bar. So that gives us our surface y, and we take the strict transform of the boundary. So this is again, it's easy to see, is again log Calabi Yau. So of course the toric variety is log Calabi Yau. This is another log Calabi Yau obtained by this blow-up construction. So that is the mirror, at least the topological type of the mirror, to this Milnor fiber. And yeah, so let me again go back to this sort of running example here. If we take this cusp singularity, then we start with P2 with its toric boundary, and we just blow up P, Q, and R times respectively at an interior point of each of the boundary divisors. So just going back to Valerie's question, this actually contains the answer as to what the matrices are in this case. So in this case, the matrices, there's P plus Q plus R matrices, and they're grouped into, P lots of one matrix, Q lots of the other, and R lots of the third, corresponding to the rays in P2, in the fan for P2.
And yeah, so that's very clear. And may I ask, so these different smoothings, do they just correspond to different toric models? Is that just the answer?
No, actually, that's an interesting question. Maybe I'm going to say a little bit more about it. But basically, when we wrote this presentation for the Milnor fiber, there was some choice involved. And that corresponds to the choice of toric model for YD. So the smoothing components correspond to YD itself. This toric model is to be regarded as some additional data. I'll say more about it in a moment, Valerie.
Okay.
Yeah. Paul?
Yeah.
Is it known at this point the situation with the smoothing components, or?
I should say, so what we don't know is there could be some exotic smoothing components which do not come from this construction. We don't know that. And I guess we also don't know that, there isn't more than one smoothing component corresponding to the same YD in some sense. Well, I mean, how to say? I guess that's the same problem. But yeah, so somehow, if you're given YD, there's a mirror symmetry construction that produces a smoothing component. We don't know that map is subjective.
Okay, I got it. So yeah, that was my question. Okay,
yeah,
thanks.
Yeah. Okay. So so here's the quick application. So if you can ask, which again is very relevant to the Green-Griffiths-Lazar-Robles application. What are the adjacencies of cusps to other singularities? And I want these again to be Hodge theoretically interesting singularities. So these will be milder cusps or simple elliptic singularities. And in fact, there was a beautiful conjecture or guess of Jonathan Weil in the 80s about how to construct such adjacencies. So what you do is you start with the minimal resolution of the cusp, and you identify as a string in that minimal resolution the minimal resolution of a Weil singularity. So remember, this is the cyclic quotient singularity that admits a Q-Gorenstein smoothing, which is sort of elementary in the sense that its Milnor number is 0, and so the dimension of the smoothing space is just one-dimensional. It's a sort of divisor if you consider how. Yeah, I'm sorry. So it's got a one-dimensional deformation space, this singularity. So his procedure was this: to apply this. So first a birational contraction of the minimal resolution, and then smooth this Weil singularity. In the process, this node at the red point, the singularity will be smoothed, and then contract what's left. This will be another cusp singularity here. So the point is, maybe you just want to emphasize, if you try to look at a general deformation of a cusp this way, it won't work because you need the sort of H1 of O to be constant in order to be able to blow down a deformation of the minimal resolution to obtain a minimal resolution of the singularity. So this won't work for a general deformation of a cusp. But if it's a deformation of a cusp to another cusp or a simple elliptic, then H1O is constant, and you can blow down in this way and get a flat deformation. Anyway, so this was a construction of Jonathan Weil of some adjacencies of Cusp singularities. And in fact, with hindsight, if we just go back to the paper of Kahler, Shepard, Barron, where deformations of quotient singularities were understood in terms of resolutions, you can show that, in fact, this procedure of Jonathan Weil generates all adjacencies of this nature for Cusp singularities. Okay, so that's very nice, but there's a sort of slight wrinkle, which is, remember, we're really interested in specific components of the deformation space. So we actually know that deformation space in general has many components, some of which do not contain smoothings, and we're just interested in a specific component associated to, well, in our context, we think of it as associated to this log Calabi Yau surface YD, or this topological picture for the Milnor fiber. So if we want to see what adjacencies arise on a particular component, we need to somehow build that data into the statement. And it's the following. So I think maybe because we're algebraic geometers here, I'll explain it in terms of the mirror. It's very simple. In terms of this...
very quickly, sorry to interrupt. So
it's okay.
Mirror symmetry, you're saying that cycle of P1s, just they have the same self-intersections. That's the YD.
So
here you have a cycle, you have numbers, right?
Yes. So the relation between, maybe is your question, if you look at the Cusp singularity, you take the minimum resolution, you get this cycle.
Right.
And the YD, it's not the same cycle, it's the dual cycle. So in terms of the matrix in SL2Z, it corresponds to passing to the transpose.
I understand. Now I remember.
Yeah, great. Yeah, okay, so in the mirror picture, this Weil type adjacency just corresponds to contracting a -1 curve of in the interior of your log Calabi Yau YD to a point. And there is a condition has to be satisfied, is that once you contract, the boundary remains negative definite. So that's the condition that this corresponds to a deformation to a Cusp singularity, as opposed to yeah, so this is the condition, I guess, that this cycle stays negative definite. Anyway, so this is a way to describe these just in terms of the mirror geometry. And so that's maybe the first hint that somehow the Kahler cone of this surface Y is going to play a role in describing the deformation space of this singularity. And so again, the picture for M, what you should think about is you have this picture where it's fibered over the disk with this number of singular fibers, ordinary singular fibers, and you just push one of those singular fibers off to infinity. That's the picture in for the Milnor fiber. And maybe, yes, I think this is what I was saying about earlier when Valerie asked about these toric models. You see, so by a toric model, I mean I have my log Calabi Yau surface and I have a blowdown to a toric variety. So that was associated to our picture for the Milnor fiber. And one could ask, well, when do two such pictures give rise to the same Milnor fiber? And or equivalently, when do two such toric models give rise to the same deformation type of log Calabi Yau surface YD? And this actually, there's a nice answer to this, which is due to Blanc, who showed that, so if you have two toric models, they'll be related by a sequence of elementary transformations. So this is an analog of the sort of Cremona result, that the Cremona group is generated by the Cremona transformation together with the automorphisms of P2. So this is some sort of similar result in this context where you have this anti-canonical divisor. But then what that means in terms of the Milnor fiber is that, if you have one of these presentations for the Milnor fiber, you can sort of move one of the singularities along its invariant line. And then, so yes, I've drawn a picture here where there's two stages. First, I take a singularity, say on this case, it's on the line corresponding to V1. I move that singularity through the origin to the other side. And so I'm pulling the branch cut along with it. But now I reverse the branch cut. I change to the opposite branch cut. And so I get this picture in the plane where I've applied the shear on the upper half plane and the identity on the lower half plane. And I've replaced V1 by minus V1. So this is a picture of the Milnor fiber. So it's the same symplectic manifold, but now we have a different Lagrangian fibration on it. So that's kind of the sort of symplectic interpretation of this. So this is the same symplectic manifold, but we have a different Lagrangian torus fibration. Yeah, so this is like a really nice thing that, now if you want to classify smoothing components, what you have to do is just look at the possible monodromy factorizations up to this equivalence relation generated by these so-called nodal slides or cluster mutations. That will give you the classification of the possible mirror surfaces YD up to deformation type, and hence the enumeration of the smoothing components of the cusp singularity. Okay, so let's see. So what I wanted to say now is I want to try to give a sense of this Hodge-theoretic description of the smoothing component. So sort of getting towards this Green, Griffiths, Lazar, and Robles conjecture. So let's just recall our notation. So we have a cusp singularity. We have a smoothing, and we let M be its Milnor fiber. And we assume this corresponds to this log Calabi Yau surface YD under mirror symmetry. And so we write down the following data. So we look at, first of all, A will be the generic Neff cone of YD, by which I mean, take a generic complex structure on YD, look at the Neff cone. That's well defined. Now I'm going to pass to a sublattice of the Picard group. I'm just going to take the orthogonal complement of the boundary components. So D is a sum of n components, D1 up to Dn. Take the orthogonal complement of the boundary components in the Picard group, which is, of course, just H2 because it's a rational surface. And B will be the face of the generic Neff cone corresponding to this supporting hyperplane. So maybe I should just say that, one could also say, okay, you take the surface YD and you contract D to a point, and this B is then the Neff cone of the contracted surface. So the contraction is, if you like, it's like a K3 with a cuspidal singularity. And so this B is essentially its Neff cone. The only reason I don't say that is actually, if you take the generic complex structure, that won't be a projective variety. It won't have any line bundles at all. So using the word Neff cone would be a little, a bit of an abusive notation. But that's maybe a useful way to think about it. Okay, and so now we also take this discrete group. So that's the monodromy group of pairs YD. So you have some moduli space of these pairs YD, which is described by a Torelli theorem, and you have an associated monodromy group. And that monodromy group can be characterized by just the fact that it preserves the generic Neff cone. And of course, so I guess there's a slight marking here in the sense that we order the components of the boundary. So it fixes each component of the boundary. Okay, so that's a group that, okay, so we don't know too much about this group just yet because, this cone can be quite complicated. And so we're looking at the sort of normalizer of the cone. This could be, for instance, there's no obvious reason why this would be, say, arithmetic or anything like that. So this could be a complicated group. Okay, so I want to try to explain now, how do you see this Hodge-theoretic description of the deformation space based on mirror symmetry? So somehow, the first thing to say is that in mirror symmetry, manifolds have dual torus fibrations. This is the Strominger-Yau-Zaslow formulation of mirror symmetry. But in dimension 2, of course, a torus is self-dual by Poincare duality. So what it means is that your mirror manifolds will be diffeomorphic. So that's an important point. In particular, the cohomology of our Milnor fiber will just be the cohomology of this quasi-projective variety, the complement y minus d. And if you just look at this, you can see that the monodromy weight filtration on M for the degeneration to the cusp coincides with the Deligne weight filtration on this quasi-projective variety U, and it's also the Leray filtration for this torus fibration, the SYZ fibration. So now there's a sort of little bit of a remedial computation of this cohomology group here. So I just wrote down the long exact sequence for the pair YU, and I'm using, so D, remember, U is the complement of this nodal curve D in Y. I take a little tubular neighborhood N of that nodal curve, and I can see that in this sequence, these terms HI, YU by duality and excision are given by cohomology groups of this cycle of rational curves. And so I finally get this exact sequence here for H2U. So there's a weight 0 part, Z, that's generated by the class of the torus in this torus vibration. And then there's a weight 2 part, which is the image of H2U in H2Y. That's this lattice Q, which is the perp of the boundary divisors. So that's why this lattice Q is relevant to the Milnor fiber. It's the graded piece of weight 2 on the second homology. And so in particular, there's an extension class of the limit mixed Hodge structure, which is an element of this algebraic torus, the HOMs from this Q to C star. So I think this was discussed earlier in Mark Green and Colleen Robles' talks. Okay, so that's the picture of the cohomology of the Milnor fiber. Maybe I just also point out as well, if you look at the cohomology of the Milnor fiber, you can see, so this torus is the radical of the intersection form, and the Q has hyperbolic signature because it's the perp of a negative definite divisor in a projective surface. Okay, so what's the monodromy in this situation? So when we look at the monodromy on the Milnor fiber, it's given by translation by a section of the SYZ vibration, this torus vibration. And this section should agree with the 0 section outside a compact set, so that this monodromy transformation is compactly supported. So it's a compactly supported diffeomorphism of the Milnor fiber. And it's given by this formula. It's this unipotent matrix. So this is the usual picture. So the difference for T minus the identity lands in W0. And the class that determines this, sigma minus sigma 0, is that corresponds to the translation by this section. So somehow this is a very simple generalization of the usual picture for a Dane twist in a 2 torus. If you have a 2 torus mapping to the circle and you think about a Dane twist, then this will be sort of a similar picture. It's an analog of T2 mapping to S1, the Dane twist in that picture. Okay, and so then there's a very nice theorem of Philip Engel and Bob Friedman that, okay, so this cone we discussed, so this face of the Kahler cone of Y is the monodromy cone for the smoothing component S. So this is the place where this class sigma minus sigma 0 that classifies the monodromy lands. So it lands in this cone. Okay, And also, when we look at this monodromy group gamma, it acts on this this cone B, which is a let's just mention. So this was a Neff cone of a surface, but it's not a rational polyhedral cone. It's got infinitely many faces, but nonetheless, this group gamma acts with finitely many orbits on the faces, and those match up using the description we had earlier of adjacencies to the expected adjacencies to cusps and elliptic singularities. So we need just epsilon more than this to actually get a space. This is the condition of Luyanger. You need to know that this group acts on the cone with a rational polyhedral fundamental domain. But let's assume that. Then we would get this Luyanger semi-toric space associated to that data. So you have a cone in a lattice, a discrete group acting on the cone with this property. Then you get a space which you should think of. So I think Valerie already said this in his talk. The best way to think about this is you take the toric variety for a fan corresponding to a rational polyhedral fundamental domain. So you look at your fundamental domain, all its translates, that gives you some nice polyhedral fan. Take that toric variety, now take a tubular neighborhood of the boundary and take the quotient by the discrete group, you'll get some space. This is exactly as we described for the construction of the resolution of the cusp. Now you contract the boundary, the proper components of the boundary there to arrive at this Luyanger space. So this is kind of one way to construct it in terms of the AMRT toroidal construction. And the open stratum, I've written it here, in this sort of tube domain description. Again, if you want to think about this in terms of mirror symmetry, this is the so-called complexified Kahler cone that appears in the Morrison story, Morrison's conjecture. So this is a space that we construct that looks a lot like the smoothing component. It has the right strata and the right incidence relations. So somehow our conjecture then, which maybe at this point is maybe obvious to make, and I think it was already made, in fact, by Engel in his thesis. I was only realized that earlier this week, is that this space is exactly the smoothing component. And in fact, so I just told you a whole bunch of stuff, and it's partly conjectural, but all of what I said is known to be true in the case where the embedding dimension of the cusp is sufficiently small. So this was a groundbreaking paper of Luyanger in 1981, where he proved this when the embedding dimension is at most 5. And those cases are easier because in those cases, the cusp is either a hypersurface, a complete intersection, or a Pfaffian. And so it's unobstructed. So there's just a single component of the deformation space, which is smooth. So in some sense, it's a little less interesting, but nonetheless, there's already an interesting picture there in terms of the description of the deformation space via this monodromy cone. Okay, so let's go back to our running example. So x to the q plus y to x to the p plus y to the q plus e to the r plus x y z equals 0. Remember the mirror. Now I just want to sort of draw a slightly different choice of the complex structure on the mirror here. I'm going to choose the distinguished complex structure. This plays a role in the Torelli theorem, where in fact, it can be characterized by the fact that the Hodge structure, the mixed Hodge structure on the open part is split for this choice. So what you do in this case is you take 3 collinear points on P2, and you blow up each of those points several times. So in general, I would take P points on the first line and P arbitrary points and blow them up. Here I'm blowing up the same point P times, and similarly on the other lines. So I just do that to show you that you can see inside the cohomology of U, you have this TPQR root lattice. So that's this, you have a root system where the Dynkin diagram has the 3 legs of lengths P, Q, and R. So these are generated, the roots, the simple roots here correspond to the -2 curves in the picture. So that's, in fact, a basis of this lattice Q in this case. Okay, and so also in this case, which is not true in general, the monodromy is generated by the Picard-Lefschetz reflections corresponding to these -2 classes. So these, under mirror symmetry, the reflections in the -2 curves correspond to the usual monodromy transformations for a degeneration with an A1 singularity. And those generate the monodromy group. In fact, that's a general fact. If you have a hypersurface, the monodromy group is always generated by Picard-Lefschetz transformations. Okay, and so now we have this action of the Val group on the monodromy cone. And it has a rational polyhedral fundamental domain in this case, which is just the Neff cone of this rational surface above. You can check that that is indeed rational polyhedral. In fact, it's generated by all the curves that are drawn in that picture. I'm sorry, so the dual cone, the cone of curves, is generated by all the curves you can see in this picture. So that's why it's rational polyhedral. There are 3 orbits of codimension 1 faces. And those just correspond to, each of the orbits corresponds to a -1 curve, which intersects either D1, D2, or D3. So that's going to correspond, in this discussion above, to the fact that there are 3 elementary adjacencies from this Cusp singularity to a slightly milder Cusp singularity. Okay, and then you can also consider the action of the Val group on the dual cone, the cone of curves. That corresponds to the action on the characters of the torus. So that is a very beautiful picture discovered by Lienga, that there the fundamental domain is just the Weil chamber. Or in other words, the dual cone is what's called the Titz cone, which is the union of translates of the Weil chamber under this infinite Weil group. And using that fact, Lienga constructs coordinates on this smoothing component S, which is the whole deformation space in this case, and it's a smooth germ, just by taking invariant linear combinations of characters, invariant for the Weil group. So you get these convergent power series in characters, which give you the coordinates on the base. And so, yes, I was just going to say that the adjacencies here are sort of rather simple, that the sort of one strata of the adjacencies are just given by reducing P, Q, or R by 1, exactly corresponding to blowing down one of these -1 curves, and you can imagine how this continues. But anyway, the point is, even in this case, this hypersurface case, is this rather complicated graph of adjacencies, or rather complex, I guess, of adjacencies to consider. Okay, and so this is the last remark of my talk, is that this description, I believe, seems to provide a highly non-trivial test for the Green-Griffiths-Lazar-Robles conjecture, that if you take the KSBA moduli space, there's a map to a Bailey-Burrell type compactification of the image of the period mapping, which extends the period mapping. And you see, why do I say that? It's because if you look at this picture, the strata for adjacent cusps should all be contracted to a point. They have the same associated graded of the mixed Hodge structure. But in the above toroidal picture, there was no fan. There was just a single cone. So there's no obvious birational contraction, at least in this sort of local picture. So somehow it's rather different from, say, the case of K3s or abelian varieties, where the toroidal versus the Bailey-Burrell, you just pass to the sort of the full cone with no fan. Here, you're going to need to do something else to show that you can actually contract those strata to a point. And I should say, I've been enjoying this week, and I haven't really thought deeply about the GGLR space, so I may be just completely wrong here. And certainly I haven't read the paper carefully, so I don't know what you know about the strata. For instance, if you have some results on negativity of the normal bundles coming from variation, curvature of variations of Hodge structure, etc., maybe that will explain this question. but I think this is certainly an example that deserves further study. Okay, so let me stop there. I think I have 5 minutes, but maybe I'll just open it up to questions.
Any questions?
So I have a question
Hey.
about this last thing you said about this test of the GGLR conjecture.
Yeah.
Somehow this should be some abstract property of this generic ample cone, right? It's like there's just a property of infinitely generated cones which says whether there would exist such a, you know, contraction, right?
I mean, maybe I'm missing something, but I just thought, you know, if you have a single cone, there's no obvious birational contraction, you know, because usually you have a fan and you coarsen the fan, and then so it comes from toric geometry. Now, of course, we're only seeing here, you know, we're seeing a sort of local picture around the stratum for the given Cusp singularity we're considering. We're not really considering these we don't see the global stratum. There's like a one-dimensional stratum where the Cusp singularity gets slightly smooth. So I was sort of thinking, you know, you need to do something like if you have some global space in a KSBA space where you have a one-dimensional stratum of cusp like that with a zero stratum, you need to show that curve's contractible. Now, probably maybe there's some reason in terms of, you know, as I said, curvature properties of VHS, you know, that has to be true. But
I don't know why. Well, I don't know why there should be, in analogy with Bailey-Borel, why there should be such a contraction, because like for the K3 case, Bailey-Borel is given by a cone, right? Which is just the whole positive.
Yeah, that's what I was saying, that somehow it looks different from the K3 and the abelian variety case. That was kind of my suggestion.
The analog of the positive cone for K3s is this generic ample cone.
That's right.
The ample cone being analogous to the actual ample cone. So like maybe the minimal object, the Bailey-Borel object, is what you're describing here as
that's
this
right. I mean, I would
semi-toroidal.
say this sort of is the analog of the Bailey-Borel, but on the other hand, you do see the extension data, the mixed Hodge structure. So it's not the, you know, so it's not the, you know, it's more like the space that Colleen was discussing, I think, in this case.
Other questions? So which paper is this included to? I mean, so
so I should say, you know, you should certainly look at Philip's paper. I believe it's called Smoothings of Cusp Singularities and Adjacencies, or ADE Adjacencies. So there's a joint paper with Friedman and Philip Engel, which describes this monodromy cone. That's maybe the key reference, I think.
So I missed the point here. So how is the monodromy around the resolution of singularities of this curve x to the p and so on related to the mixed Hodge structure of the pair YD?
Well, you know, all I was saying there was, you know, so first of all, when you do SYZ mirror symmetry in dimension 2, it's topologically they're diffeomorphic, the mirror and the original variety. So the cohomology is identified. So that's a way to get your hands on what the cohomology of the Milnor fiber is. And in fact, you can see that the weight filtrations also correspond.
Which one to which one?
Well, so on the Y, you have the, you know, the Deligne weight filtration on the open part.
Yes.
And on the Milnor fiber of the cusp, you have the weight filtration of the limiting mixed Hodge structure.
So which paper, this is in your paper with Alicia or in the old?
No, I mean, I this is not a deep thing, I don't think. I mean, you know, it's just, you know, everything is determined by the class of the torus. And, you know, when you do this diffeomorphism, the torus...
It uses mirror symmetry, right?
Well, I mean, this topological statement is rather simple. I should say, you know, I mean, you don't need to use any deep mirror symmetry for that. I should also mention there's an alternative approach, which was the original approach of Lienga and what Philip and Bob do as well, which is you can compactify the Cusp singularity. You can take a Cusp singularity and you can put it on a proper but non-Kahler surface.
Okay.
And then you can look at sort of variation of Hodge structure for that. I mean, so it's non-Kahler, but you can do Hodge theory in this case, and you can look at the variation of Hodge structure from that global point of view. I didn't want to do that in this talk because it's rather confusing how it relates to the.
Can you finish? So you take
Yeah.
this symplectic surface, and then what do you do with it?
Well, okay, so there's a surface called the Inoue surface. Topologically, you take the link of the Cusp singularity and you sort of suspend it. So you have 2 points, one of which, in the complex analytic description, one is the Cusp singularity, one is its dual. So the cusp and its dual have isomorphic, diffeomorphic links with opposite orientations. You can glue them together to form this surface. And then what you do is, you resolve the dual cusp and deform the cusp itself. So you can show there's no local to global obstruction. So any smoothing of the cusp is realized on this global surface.
So what is this mirror to?
The Inoue surface itself, or yeah, I don't know, but I mean, maybe there's this paper of Abby Ward. Maybe it's related. She has this with Denis. She was working on mirror symmetry for hop surfaces.
Yes.
Quite similar. I think it's worth investigating. Yeah, but I don't think we haven't studied that. But what you can do, you see, if you deform the Inoue, you get this nice projective surface, and that's mirrored to the Milnor fiber. So that's a Stein manifold.
Yeah, I got that. And so where is this Inoue surface construction?
So it's in the original paper of Lienga. It's Annals 1981.
Okay. I know.
Yeah.
The construction of the Inoue, it's the exact same as the construction of the Tate curve, of the universal cover of the Tate curve. So you glue an infinite number of toric varieties together, of C squareds, an infinite type toric variety, and you quotient by Z. So this constructs on the region where it's properly discontinuous. The quotient is this Inoue. So
where is this? Sorry.
This is in maybe, I think it's in Inoue's original paper, maybe. Or maybe it's a well, I can send you a reference later. There's another reference where it's even clearer written.
That would be fantastic. Thank you.
But yeah, so on the open torus, C star squared gets quotiented by this integral matrix, but you can view it as being quotienting it by the transpose matrix. If you change the basis by an orientation reversing thing of Z2. So you can kind of glue 2 Tate curve constructions together to get a surface which has the 2 cycles.
Philip, I also want this reference.
Sorry, was the question about a reference?
Yeah, you promised.
I know. Yeah, I'll try to find it. But it's a Japanese mathematician, maybe from 1980, but it's not Inoue. It's somebody else was writing about this duality of cusps.
Yeah, that would be.
It might be Nakamura. Yeah.
But unfortunately, there are more than one. There's more than one Nakamura. So.
Yeah. Right. So that's a good. It's Iku Nakamura.
Okay.
Yeah. So maybe duality of cusp singularities by Iku Nakamura.
Ah, I see. That's good.
That's very nice, and it works for the simple elliptic case. So there you get an elliptic curve and a cycle of -2 curves instead of a contractible cycle as the 2 opposite ends of your type 7 surface.
Very good. Other questions or comments?
Paul, can you say what would be the easiest case? I mean, the first test case where I could take a concrete cusp and test your.
Yeah, I think this was kind of what I realized, is that somehow you don't have to do anything complicated. Just take any hypersurface cusp that has a non-trivial adjacency, then there's going to be this problem or this question, can you contract this stratum? So do you understand the picture? You'll have a zero-dimensional stratum corresponding to your cusp, and then you'll have some higher dimensional strata which correspond to partial smoothings of the cusp. And according to GGLR, you should be able to sort of crush that to a point. So, I think the simplest thing would be just find a cusp that deforms to one other cusp. And so then you'll have, a point and a curve, and you want to show that curve is contractible in the KSBA space. As I said, maybe there's some Hodge theory reason why this always works.
All right, fantastic. Thank you so very much.
Yeah, you're welcome.
Fantastic talk.